Okay, so we can get started. Okay, so let's get started. All right, second half of the course. So just some look ahead, right? So the midterm is nice and settled behind us at this point. The grades will be released immediately after class, and so along will be your answer sheets and the answer key. So what's coming up ahead? We got Bomb Lab, right? So just in terms of what's coming up ahead, the next quiz 6, which will be some of the concepts behind assembly, so just some data movement, transforming loops into assembly code, this type of stuff. That's going to be in quiz 6. That's going to be released tomorrow morning. That will be due in just a little bit over a week, so next Friday. The stuff that we're covering for the next couple weeks is in this menu here. So this is kind of a rough correspondence between what the topic is, what chapter of the book it's a part of, and then which piece of the Bomb Lab it's relevant to. So it's a good idea to follow along at least with this schedule. So definitely by the end of today, you will absolutely have everything you need to be able to get through phase 1 of Bomb Lab, if not a couple more, right? Phase 1, phase 2. It would be a good idea to stay ahead. You will notice that right now the Bomb Lab PA4 is configured to be due March 29th. That will be pushed because just by this estimate, it's very clear that we won't be able to get done with the contents relevant to the later parts of the Bomb Lab until April 2nd. But this isn't an excuse to not touch Bomb Lab whatsoever over the next week, right? Don't delay. Get started right away. Good. So those are the deliverables ahead. If you want to know kind of how this impacts the other programming assignments for the rest of the semester, the syllabus on my personal webpage, the long-range syllabus for the class, has also been updated to reflect what the rest of the semester looks like. Yeah?
Is it being pushed to April 2nd, or is that date undecided?
Undecided. Yeah. Okay, any questions about logistics? So who's at least taking a look at Bomb Lab? Who's got phase 1? Good, right? That's good progress. So just before we left for the break, the Thursday before the break, I've done a quick walkthrough of getting started on Bomb Lab and getting started with the debugger. That was done just kind of with no notes, just directly from just kind of demonstrating. So this is the set of notes that demonstration corresponds to. So what we'll do is, yet again, maybe a 20-minute quick start of just getting started. And this time around, some of you have actually seen a little bit of this, so this could be a little bit more interactive, right? So if you see stuff along the way that you want to pick a question about, happy to field questions here. So the goals of Programming Assignment 4, Bomb Lab, right? It's the secret kind of main learning goals is for you to be comfortable with text-based, command line-based tools such as the GNU debugger. You'll get to see how in assembly, what the computer is doing, it doesn't have these notions of loops or switch statements or function calls, things like that, but rather all of those higher level language constructs that you're used to, they are all supported deep down from pretty simple not super complicated assembly instructions. And these build up, allow you to do comparisons, allow you to create loops, allow you to create function calls. This is a broader set of skills called reverse engineering. So given something that's been compiled, given something that you don't have the original source code for, can you deduce some information about it? So what you want to do is obtain the BOM package from the web server. You can follow the PA4 instructions on how to do that. And I've been doing the demonstration out of bomb1.tar, the first bomb downloaded from the demo website. And what comes in the package is you get a not very useful at all top-level source code. Right? And this just gives you the skeleton of what the bomb is. It's got several phases. Your goal is to pass through each phase without having the program call into a function called explode bomb. We got some questions on Piazza already around kind of the logistics of this. If you, in the process of working on your bomb lab, detonate your bomb too many times, well, learn what you can from the one that you have, download a fresh one, and we'll grade the fresh one, the last one that you successfully solve. Good. There was also another question on Piazza on can you make notes or take notes on the source code if you want to link to some citations that you found in helping you solve this programming assignment? Sure, you can take notes on the bomb.c source code. Yeah.
So if I, like, for example, I explode my bomb once, right? Can I get a new bomb and then just completely redo it and still it be graded as if I didn't explode it?
Yeah. Yeah. Why not, right? What's the purpose of otherwise? So long as you learn the, the objectives, right? Again, back to the objectives. If you learn these skills, then that's good. Okay, so already off the top of the list of things that we can do, you can already get some basic information about the bomb. So one thing that you can get is called the symbol table. So that is invoking the object dump command -t to get the symbol table. And the symbol table basically we'll take a look at the symbol table, is basically a matching of addresses, right? So these are address numbers to the locations of various function calls, right? So these function calls, like invalid phase, phase 1, they have offsets relating to each one of them. And the symbol table records that. You can also get the best effort disassembly, so taking the binary, taking the bits and bytes, and undoing them, right? Try to get back the assembly by invoking object dump -d to bomb.s. And this is going to be the best effort of disassembly, right? It's like looking at the bits and bytes of the bomb binary, and it knows how to group the individual bytes in the order that makes sense to interpret it as assembly. And it's taken that assembly machine code and written down the instructions and the arguments corresponding to the binary. And with this, you can also see that there's various labels, right? So the labels here of phase 1, so phase 1, phase 2, phase 3, this is what the symbol table was recording, right? So it was saying that phase 1, it has a number. It is this many locations farther into the assembly. That's what the symbol table records, right? So starting with this part of the assembly, this is the instructions that implements phase 1. And then finally, the last piece of additional information you can kind of just extract off without even touching the BOM directly out of the BOM binary is you can extract the human readable strings, right? So it'll take a look at the binary, look at sequences of the binary that looks like ASCII text, and write down that text. So this tends to be, right? So this tends to be strings that exist in the source code, right? So if you have the source code and there's a printf statement, the printf statement has quotation mark, a sequence of ASCII text, that becomes human readable code inside the binary, and this can extract all of that out from it, right? So inside here, you'll see various things like error messages, congratulatory messages, and so forth. Good. Any questions on this slide? Yeah.
So throughout the little disassembly thing, I kept noticing these little comments with 4-digit numbers. Do they correspond to things strings?
Let's see. Can we really get that kind of front-to-back connection? I don't know. So you want to see an example of this? So your hypothesis is that maybe, what do you want to pick on here?
Maybe 3088.
You want to do 3088. How about this, 3439? Right? What's 3439? What does this correspond to?
That's our little input thing, isn't it?
It's a string, printf format string of 6 integers, right? So let's see. Your hypothesis is, does this 3439 correspond to anything in what? The assembly or the symbol table?
In the object of the BOM.
So the assembly, disassembly. So here I have the disassembly bomb.s, and I was looking for 3439. Let's see. So we found one there. So it's got these. Here is a comment, as you say, right? So it's possible that this corresponds to that string of printf format string of 6 numbers. Let's see, where else does it? Yeah, so 3439, it only shows up once, right? So almost certainly it has some kind of connection to it. Any questions, other questions about this slide here? Okay, so let's see. So this is just kind of a tutorial on the way to think about how to tackle bomb lab, right? So this is the, what I have on the slide now. This is never mind. So what I have on the slide here, this is the assembly for phase 1. This is not going to be necessarily the assembly that you get for your BOM, or not even BOM 1 that I have on the right-hand side here, but rather this is the default BOM that everybody can download from the textbook website. And this is the entire assembly, right? So the way to think about what we're trying to do is you have this instruction here that says call Q. So Q means a 64-bit memory address. Call this location, which corresponds to the function called explode bomb. So in other words, we want to make this instruction not take place, right? We want to skip over this line. So how do we skip over that line? Yeah.
The line above is JE, which means jump if equal. So you need to like compare 40EF blank
Yeah, so jump equal, right? So the first argument given to jump equal, this instruction, is 400EF7. So 400EF7 is this line here. So that's immediately, the program counter is beyond call Q, right? And then here it has a little annotation, a comment, if you will, that says, well, what is this 400EF7? What does that correspond to? That corresponds to phase 1 at 0x17 beyond the beginning of phase 1. So if you count from phase 1, this address here, 0x17 beyond that, will be this line here. So we want to, it's good, right? So we want this jump if equal to take place, because that will get us to skip over the explode bomb instruction. So then how does jump equal take place, right? So it's not today's lecture, but we'll talk about this on next Tuesday, how exactly jump equals takes place. But yeah, you want to give it a try?
So it looks like jump equal is determined based on the test value. And if I'm not mistaken, that test value runs a bitwise AND comparison between the two things provided.
Yeah, so that's a preview, right? So Tuesday's class will be exactly what that's doing. So we want to do something, right? We want to do something so that test will inform jump equal to, yeah, go ahead, do the jump. And what does it test upon, right? So it tests upon EAX against EAX itself. And this is an important piece of information of the special property of the AX register. So EAX, by convention, EAX is the return type from functions. So this line here, right, we're stepping backward and backward, right, rolling backward, backward engineering to get to this point. EAX is going to be returned from this call here, right? Call Q, it calls a function called strings not equal. Strings not equal is a C function. Strings not equal returns something, right? It returns whatever it is. Its return is going to be stored in the register EAX. So we want strings not equal to return the value 0, right? So this is the thought process of how to diffuse phase 1. Any questions on this slide? This may be familiar to some, but this is fresh information to others. Yeah.
If you call test on like any number in itself, wouldn't it always return 0?
Exactly what test does, we'll come back on Tuesday.
Okay.
Yeah, you can preview the slides, which will be posted right after class, or you could check the textbook slides too. It also talks about it.
Okay.
Yeah, and ultimately it's from the textbook. Yeah.
No, I was gonna say like, because like if it's 0 and 0, that's like false and false, which is false.
Yeah. Okay, anything else about this slide? So again, right, so 10-minute recap of the Thursday before break. Some of the steps that we did to set up our environment. What we want to do, we don't want to just directly invoke the bomb, right? It asks for a string to input, and there you go. It's not the answer that it was expecting, so the bomb blew up. So instead, what you want to do is you want to invoke the bomb in the debugger. And within the debugger interface, there's some helpful getting started instructions to the debugger that can help you. So you can always say help. It'll give you context, useful context, useful information for the context area that you're in. We want to change the layout we're seeing here. And if you read the layout instructions, the manual for different layouts that you can set up, what you can do is set toggle through different modes of displaying. If you just hit enter while you're at the command for the debugger, that will repeat the previous command. So the previous command I had was layout next. So hitting enter will just do hit layout next again. And this is a good view to put your debugger in, right? So up top, you'll have your register values. In the middle, you'll have your assembly that the program is at that point. And the view that shows you the source code is useless, right? Because in this program that you have, you don't have access to most of the source code at all. Good. So the first thing that you want to do is you want to set breakpoints at explode bomb to make it so that when it hits the line of code, when the instruction pointer points at explode bomb, somewhere in explode bomb, it will hit a breakpoint, right? So your program execution will stop at that point. And given where you are in the assignment, you'll want to set breakpoints at the part of the bomb lab that you're at any given moment. And finally, one of the convenience features is you can also run the bomb by giving it an argument to a text file that records your solution so far. So this would look like in a couple different things, right? So this would look like if you were on the original bash command line, you say bomb, and the argument is mysolution.txt. Or within the debugger, this would be like you have the instruction to run the program, start running, but you pass it an argument to the run command. So there's a slight gotcha that has taken place before, which is so the takeaway here is in Unix-based computers and in Windows-based computers, there is a very slight difference in the convention of what the line ending determinator is, right? So some of you would have encountered this, and people have had this problem before in past years where it looks like this is all correct and the text files is exactly correct, but for whatever reason, the bomb keeps exploding even though this text file is correct. And this gotcha is oftentimes because if you're doing this in Visual Studio Code, Visual Studio Code, VS Code, has this very evil button, just a completely unnecessary feature where, let's see, I need to log in. Can't see. Has this feature where in your text editing field, there is a button that sets the line ending character, which I don't really understand why they make it such a prominent feature. So over here, this button right here, see where I hover over and says LF? So LF is the Unix mode of line ending characters. And you can just very easily accidentally press this and toggle to CRLF, which what that would do is suddenly your programming environment, right? Your text editing programming environment is configured to adhere to the Windows, the Microsoft Windows mode of ending lines. And this would mean that the invisible characters that represent the end of line is now 2 characters, and from the bomb's perspective, it means that your string does not match, right? So this is just hopefully nobody, well, I'll take 2 minutes to mention this here, just to hopefully that nobody gets stuck on this bizarre problem, right? Invisible characters can cause problems, yeah. Oh, you can't see the button, okay. So let me shrink this up. So the button is this here, right? It makes no sense that this is such a easily triggerable feature. Yeah. Yeah.
So you want it on LF or CF?
So you want to set it on LF, right? And some of you are doing it in VS Code, some of you are not. This is only relevant if you're using a high power programming environment such as VS Code. So LF line feed is the convention that is used for Unix-based computers, so this includes Linux and Mac OS. The other convention is for Microsoft Windows. Yeah.
Regular text editor also just, at least in my computer, automatically added the \r.
Yeah, so it's a setting. Most of your text editors will have a setting that allows you to change that setting. Yeah. Okay, so back to the slides. Right, so that's setting up your solution file that records your solution so far. So now you can run your program. And so here now we're in the phase 1 part of the program. And there's various ways for you to allow the program to continue. So continue will let the program free run all the way to the next breakpoint. Next will step through the code, will step through the assembly line by line, right? So it will step through the assembly line by line, and when it hits a call here, so here it's about to call the function called strings not equal, right? It's about to call the instruction strings not equal. And so next will step into that function so that when you look at what's happening, what we're looking at in the assembly here, right now it's displaying that we're in phase 1. I do next and it should have called into, oh, whoops, I explained that backward, sorry. Next will skip over the call into. Step will call into the function, right? So if I did step we would have descended into strings not equal here. Questions about this slide? Yeah.
Does the name of the solution file matter?
Name of the solution file doesn't matter. Okay, so some other important features that we want to have, right? So good. Good, right? So some of the features that we want to be able to do now is we want to be able to inspect our environment. So there's a few things that we can do. You can print registers. So there's an instruction that says print, please print the register value at EAX. So, or you could also just in this view here, right? So in this view that we have our debugger set up right now, you can also just see the state of the processor, the registers. So here it says, in your processor, these are the main registers that programs run with. And it's saying that at this moment in the program, it's executing the instruction at this location corresponding to an instruction within strings not equal, right? And the state of your processor, here they are. The value that is stored in the A register, the AX register, or the EAX register, or the RAX register. Remember, these are all the A registers, but just different lengths of that same register. what's being stored right now is this hexadecimal value, 0x555 ending in 9720, right? And that's the hexadecimal number. It also displays the decimal number alongside it, so you can see what it is. These memory locations, typically, the number is not going to correspond to anything meaningful, but some of these values, sometimes they have human-readable numbers, right? They're small values that are significant. So you can test this, right? So we can say, please print EAX. So it will say EAX. EAX is a certain value. Or we can say print, show me RAX. It will say it's a certain value. So here it says print RAX. This number here, what's being stored in RAX, is exactly what it reports. Or you may want to have it print as hexadecimal, right? So by default, it says it out as decimal format. You can say print \x will force it to report it in hexadecimal. And all of these print things are relating to just looking at the register set, right? So here, there's one thing I kind of want to emphasize. This is useful information, right? Useful information here. We're in a function that's called strings not equal. And I've hinted at already that functions, here's a function called strings not equal. It's a C function. It returns something. The convention is that return will return through the A register, right? Another part of that convention, which is useful to know, is when we call into functions. You know how functions have many arguments, right? Strings not equal, we'll have the first argument, we'll have a second argument, we'll have a third argument, and so forth. The convention called the application binary interface, ABI, for how function calls work, how it sets up the memory stack, is that the first argument to a function is expected to be in the DI register, right? There's a sequence of this called the DI register, stores the first argument, SI register stores the second argument, and there's a whole set of these conventions. Yeah, you had a question?
I couldn't help but notice, but I remember reading that RAX was essentially a 64-bit version of EAX. If that was the case, would that size difference be the reason they're printing something different?
Yeah, so good eye, right? So what you're referring to is the printout here and this.
Yeah, that's what
Right, so I gave an example of printing out RAX, and at first I did print out EAX. So RAX is what the interface tells us, right? It tells us default RAX is this value. So RAX is the 64-bit version of the AX register. Processors were not always 64-bit processors. There was a time when Intel's instruction set architecture was 32-bit, and when it was in the 32-bit era, the AX register was called the EAX register. So you can basically take this register here, and if you want to print the whole register, you print RAX. If you want to look at the 32-bit subset, you print EAX, right? And you can confirm, just to make this clear, you can confirm that if I grabbed, this is how many characters here. Can't really eyeball this right now. But if you printed the 32-bit subset of this RAX register, this is this value that was reported here. Okay, so calling convention, right? Calling a function, the first argument will be a DI register, second argument will be an SI register. So what should we inquire already at this point? We just called into a function that's called strings not equal. What are the strings? How might we find out? You want to give it a try?
You can print the registers, the DI and the SI registers.
Okay, so let's print RDI is the first argument, and it's this number, so it looks like a big number, right? So maybe let's inquire it not as a decimal, but rather as RDI printed out as a hexadecimal there. Good, right? So it looks like an address. How do we get to the contents of the address? Yeah.
The address is the address of the RAX register.
So let's pause there. So you said the address of the RAX register.
Yes.
The RAX register doesn't have an address. It stores an address.
What the values at the RAX, like
Yeah.
the same value.
So the RAX register is a register in the CPU. It holds a value. It holds this value right now. That value is an address. It's a pointer. Right? So now we want to chase down that pointer. The pointer, this number, refers to a location in memory. And you've got an instruction to the debugger called the X instruction, which inquires a address location. Right? You can think of this as dereferencing the pointer. I've got a pointer value here. Tell me what's at that memory location. So you can say X right? So it says X at RDI is this value here, right? It's this value here. So this just looks like a number. You can also modify the commands to print at different formats. So what this will do is now instead of treating this location as just a single number, but rather let's treat it as a string. Let's treat it as a string, right? So you can do X as a string, the location at RDI, what's being stored in the RDI register right now, and there it is, right? So here is a string that's being compared for the strings not equal function. Okay, any questions about this slide here? Yeah. Why did RAX and RDI have the same value? There's no particular reason. So that's a valid question, right? So I say, convention is when you exit one function, the RAX should store what that function returns. DI should store what the next function call is about to the next function that's going to be invoked, what's the first argument. So a reasonable guess, I can't confirm if that's exactly why, but you can imagine a situation where in the source code, there was a previous function called input strings. Input strings returns a string, and immediately after input strings, the next call in the source code is a call to strings not equal. So you can imagine, right? Input strings return the string, which then is an argument into strings not equal. The compiler says, well, these two functions, the return from the first function then immediately becomes the call function argument to the next function. So that would explain why here you see RDI and RAX are the same address location. That could make sense, right? That's reverse engineering. You're noticing these patterns and trying to figure out or think about, so what's the source code that would lead to this pattern? Anything we should try here or questions about this slide? Yeah.
I was going to ask, strings not equal, that has only one argument, or are there more arguments?
Good, let's experiment, right? So where's the second argument gonna be? So RDI has the first argument. Where's the second argument? Yeah. Yeah, so let's do exactly the same, RSI, and there is a convention here, right? So what I did here, the last call to X, I had configured it to print as strings, and now I invoked the X instruction again, now with a different register, and it assumes, right? It continues the previous setting of printing things as strings. So here in RSI, a different memory location here, you see up here, it is also a pointer pointing to a string. The two strings are the same. Why? Why are these two strings the same? Yeah.
Because you inputted the same string. Well, because like you inputted that string.
Yeah, because I invoked this
like,
already
one
with the
was
answer.
your input, one was the actual answer.
Right.
You put the same string.
Yeah.
I had a question.
Mhm.
So you notice RSI and RDI because of the two move statements, correct? Like at plus 8 plus 11.
I know of RDI or RSI because of the move statements. Let's see.
Was RDI/RSI in the original like phase 1 assembly?
We know it's RDI and RSI because that's part of the ABI, the application binary interface. The convention of how functions are called in x86 machines on Linux is that the first argument to a function is RDI, second argument RSI, and so forth. But yeah, if you did not know that information, right, that interface, you could have deduced the same by looking at how the assembly is shuffling around the contents of RDI mentioned here, RSI mentioned here, right? Good question. Okay, so that was basically quick start, right? Essentially phase 1 of the bomb lab. Now we've got some tutorial or examples to study 2 more demo codes. One is called addressing modes. Right, so addressing modes is all about, let's see, I need to recap it real quick. So far, in PA4, there is a folder called Assembly Basics. Thursday before break, we studied this program called swap.c, which is just this tedious study of all kinds of different swap statements. I was swapping different data types, right? So I swapped characters, I swapped shorts, I swapped ints, I swapped longs. And the takeaway of this demo code was that when you swap different data types, the way that swap is implemented as assembly, the way that each swap function is implemented as assembly is through these move instructions. And the source code, right? In C, we have this notion of data types. Data types they might be 8 bytes long, maybe 4 bytes long, maybe 2 bytes long, and so forth. How does assembly know what data type it should work with? That assertion or that intent is conveyed from your source code through the compiler. The compiler sees you're swapping 2 longs, so it picks the correct version of move, right? So move has all of these different flavors. It has move Q for long integers for 64 bits. It has move L flavors, such as this one, for 32 bits. It has move W for word for 16 bits, and it has move, what's the one for character? Move B, I think. Move B. Yeah, something along with move B, right? Move byte for single bytes. And so here you could already kind of see kind of the slight short-sightedness and the historical perspective, right? Intel engineers set out to make the 16-bit Intel processor, and they said 16 bits is going to carry us into eternity, right? And so they called the move word instruction move W, because all words are 16 bits, 2 bytes. By the time that 16 bytes was not enough, and they set out to engineer the first 32-bit Intel processor, they were like, well, what's a 32-bit word? Well, it's a long word, right? So let's call 32-bit instructions move L for long, right? But now long is not that long anymore, ever since 2004. And then so instead, finally, in some ways, the convention for what the 64-bit instruction is called, move Q. Q stands for quad word, right? 4 words, 4 times 16, 64 bits, is what they call the move instructions for 64 bits. Some of the other takeaways from this first demo code, right? So this demo code is swap.c. Some other takeaways was, how does the compiler know, and how does the compiler enforce signed and unsigned integers? Well, that results in different choices too, right? So here we have, let's see, do we have an example of that? So you can create an example of, suppose you were going to swap or move a signed character into, you were going to move an unsigned character into a signed data type, or move a signed data type into an unsigned data type. It's going to have to pad additional bits at the beginning of the number, right? And the padding of what those bits should be has to be correct to enforce the signed and unsigned property of the number. So you can observe, right? If you toggle between different versions of signed and unsigned, it will choose between different flavors of move yet again. So there's different flavors here of move Z and move, what's the other one? Yeah, move S. So move Z, move S, that distinction enforces signed and unsigned conventions, right? So that was in the previous set of slides. That was recap. Anything I can say here to clarify what's the main point of this? Okay, so the next couple demo codes, one is called addressing modes. Okay, so what is addressing modes? Addressing modes is, you see it right here. So here is a move instruction. It's going to move from a place to another place. So move from some place specified in the register to another place specified by a register. But within the instruction, you've got this peculiar syntax here of a parenthesis, right? And this is a kind of addressing mode. So the next chapter of our slides here is talking about what does that mean when you have the arguments to an instruction having these different syntax annotations telling where the location is. So here is the different modes of addressing. So let's look at this slide here, right side of this slide. This is taken from the textbook slides, the CSAPP textbook slides. And what it's saying is you have your move Q instruction, again, Q, quad word, 64-bit words. And it can move from a location to another location, right? And the way that the assembly instruction will be written is move Q is the instruction. The first argument is move it from where and to where as the second argument. So there's now these combinations, right? You can move from different places and to different places. And there's three different types of places. Three different types of places. One is called immediate, so constant values. Another is called register, so the location is the register. And the third one is memory. It's a location in the main memory. What's the difference between register and memory? Conceptual question. Where do registers live? Yeah. Registers are the CPU, right? They're the front of mind. They're your consciousness. They are what the processor is aware at that moment. Where does memory correspond to? RAM, random access memory, main memory. It's what we refer to when we say your memory has a segment called the stack, it has a segment called the heap. Right? There are two different locations. There are different places in the computer hardware. Registers, again, correspond to the consciousness. Memory corresponds to memory, right? Your long-term memory or your short-term memory, but not whatever is front of your mind at any given moment. And so already, kind of with that rough analogy to human cognition, neuroscience, we immediately notice there's three types of locations, three types of destinations, but how come not all combinations exist, right? Here it's saying that I can take a constant, immediate constant, I can put it to register. I can say, I'm going to think about it right now. I'm going to think about the number 4. Or I'm going to memorize the number 4, right? And so the missing combination here of I have this constant value of 4, well, you can't somehow store 4 into 4. It doesn't make any sense, right? So, okay, so you can't move source, a constant, into a constant destination. Right? Constants cannot be destinations. Okay, source, right? Register. My front of mind, I'm thinking about the number 4, and I can somehow think about the number 4 in different ways, or I can memorize the number 4. That makes sense. And again, you cannot use constants as memory location destinations, right? So destination cannot be immediate. Finally, source memory. I can pull some number from my long-term memory, from the main memory of the computer, and I can move it to the front of mind. I can put it in the CPU for processing, right? What's missing here? What's the missing combination? Yeah.
Memory to memory.
So what does this mean, right? So this statement in red here says that you cannot pull a number from main memory and put it directly into main memory. Why not? Well, first of all, could that be useful? Yeah, right. It could be useful. It may be a useful thing that I can take some, in one instruction, take some value from one place in my main memory stack and put it somewhere else in the main memory stack. But why is it not enabled in our view of computer architecture? So just in case you're lost, right? What are we pausing on? What is the underlying reason that this cannot be done? Any action has to go through the CPU first, right? That's exactly right. And this is all modern computers are built in this von Neumann standard architecture where the CPU is the boss, right? The CPU puts stuff into memory, takes stuff out back from memory, and the memory is just there to hold on to things. Memory cannot somehow move information around within its addresses. It has to come through the CPU and be put in the right place. right? This is just like in human psychology, right? You can't have one long-term memory somehow get stored at a different long-term memory. You have to think about it in the front of mind to create new memories, right? It's kind of like that. It's a very rough analogy. So that's why there is no move queue instruction mode, addressing mode, where the source is memory and the destination is also memory. Okay, good. Right, so now let's look at the syntax. Right, so the syntax of how the instruction is written out is if it's a constant, well, the constant is written out as a constant, such as that. That's a constant value of 4. If it's a register, well, the register is written out like that, right? RAX register right there. So any guess on what this means then? So this syntax shows up in memory format. Right? It shows up when the source or the destination is main memory. What do you think this corresponds to? Yeah. So what do you mean pointer to the register?
I guess like the pointer in main memory to the register is 8.
So let's use correct phraseology right there. So the value stored in the register, the value stored in RDX is a address location. Putting it in parentheses is like saying I have an address stored in P. Let's dereference that address. So it's saying that the address that is stored in RDX, let's go to the location at that address in main memory. Right, so parentheses simply says treat the value as a address location. Okay, any questions on this slide? Yeah.
So the parentheses is essentially specifying that it's dereferencing.
That's right. Right, it's saying we've seen this already somewhat in here. So to tie this to our demo, right, this is saying that I'm interested in seeing what is the location at the RDI register. So this is the address location. Putting that in parentheses refers to the memory location at this address. Yeah.
What does the dollar sign do?
What does the dollar sign do?
Like the percent.
So percent refers to registers. Dollar sign is a syntax meaning that it's an immediate value. Okay, so good, right? The next part of this study, right, the next thing we have to dive into now is in the memory format, right? So in these parentheses, when these parentheses refer to memory locations, the complications or the complexity doesn't end there, right? There's a little bit more to it, right? So you can have instructions which are referring to memory locations, but they'll do some cooler tricks rather than just putting in parentheses. So these are the next additional addressing modes. Addressing modes of taking a register and referring to a location in memory. Right, so far we've already seen one. So far in the previous slide we saw normal mode, where you have your register value, you put it in parentheses, and that refers to the location in memory. There's additional ones, right? So in assembly, you'll also see instructions that look like this, where instead of just putting it in parentheses, now it's got an 8 put in front of it. Right? So what does it mean for it to have an 8 in front of it? Any guesses? Yeah.
Grabs the value at RBP and then adds 8.
Yeah, so this is kind of the part where assembly is kind of really annoying. Right? So what you said is correct, it adds 8. Now, this is very annoying, right? Because why wouldn't they just make it look natural to human beings, we see this 8. It's put in an 8 ahead of a parentheses, ahead of a value. So any reasonable person would say, aha, that just means multiply by 8. No, that's not what they meant, right? So this is called displacement mode, and it means take the address location stored in RBP and add 8 to that, and then go to the memory location. Why is it this way? They designed it that way. It's not like floating point, right? The thesis of the floating point chapter, if we were to design floating point today, it would be the same. If we were to redesign x86 today, many different things, many different choices would be equally valid. And this is an example of that. So in what context would this be useful? So what types of situations would we have? I have a memory location, and I would like to add 8 to it. Yeah.
If you're like trying to access a different element in an array, maybe?
Sure. So I would like to access a different element in an array. I would access, I've got an array location stored at RBP. RBP refers to the beginning of the array. So what types of scenarios will we want to access 8 bytes into the array? Yeah.
Storing characters, like a string.
So if you were to store characters in the array, so how long is a character? 1 byte. So here, this is referring to 8 bytes, right? Yeah. Oh, has your hand raised?
I guess like 2 integers.
2 integers, good, right? So 2 integers would be 4 bytes. 2 times 4, that would be 8 bytes farther along into the array. So that could be a situation where you have this part here, 8 bytes beyond the beginning of an array. But there's additional clue that you have to take into account, right? This line of assembly here, there's yet one more piece of clue you have to take into account. What's that clue? Yeah.
Because it's like moving into the cursor would be like a pointer.
So good, right? So there's all kinds of these clues here that tell you what is the data type being moved into this location, right? So clue number 1, what's the flavor of move instruction involved here? Yeah.
Quad word, move Q.
Quad word, right? Move Q flavor means move quad word. Each word is 16 bits, 2 bytes. So this is moving 64 bits at once. It's an 8-byte move. What types of data types correspond to 8 bytes again? Yeah, over there. Doubles and longs, good. So that's clue number 1. The other clue, where is it moving it to? It's moving it to the R flavor of the DX register, right? The very latest version, 64-bit version of the DX register. So it's saying that this move here is moving 64 bits. It's moving 8 bytes at once. So if you see that, and it's saying 8 bytes beyond the beginning of a location, so this kind of hints at us what is the type of array that it's dealing with here. Could it be an array of regular ints? No, right? Most likely, this is referring to an array of longs. Each long is 8 bytes, and this 8 comes from one index into an array of longs or an array of doubles. Does that make sense? Anything I can say here to clarify that chain of logic I just outlined? Yeah.
So if we wanted to move integers, it would be 2 instead of 8.
So if you were to move integers, good, right? So live exercise, right? The claim here, corresponding to this code here, is this is useful for accessing array element 1, right? Array element 1 is one element beyond the very first one. It's beyond array index 0 of an array of longs or doubles, right? That's what that assembly would correspond to. I want to grab some element from an array, put it into a temp variable. Now what you're proposing is, what if we want to work with an array of ints or floats? So let's try that, right? Let's as an exercise, what would that assembly look like if I were accessing array element 1, store it into temp, where the array is an array of ints or floats. So first of all, which flavor of move?
Sorry, for which one?
For ints. For now, we're moving int from an array of ints into a temp variable. Would it be move q? Move q is quad word, so that's long ints, longs. Yeah.
W?
Is it move w? So w is when they were short-sighted and first set out to make 16-bit processors, they said words are 16 bits. That's the end of the day, right? And then one day they made the 32-bit registers. They said, okay, great, we'll call it long words. And today, long words are not that long anymore. So we call them quad words now for 64 bits. So long word refers to the 32-bit version. Why? It's just the way it is. And we're going to, our array is beginning at the location stored at RBP, right? And now we want to access array index 1. Array index 1 is how many bytes beyond the beginning of the array? Yeah. 4 bytes. So what should I put here to indicate 4 bytes beyond the beginning of the array? Yeah, just shout it out. 4, right? And finally, to keep the whole line of code consistent, what's the valid flavor of the DX register that I can move 4 bytes into? RDX is the 64-bit version. Yeah.
EDX?
Yeah, EDX, right? And you can think of them as, why do they call it EDX? Again, all of this is short-sighted, right? When they designed 32-bit, they said, let's call it the extended DX register. Well, these days, extended is not that extended anymore, right? So why do they call it the RDX now? I don't know why. R stands for whatever. So this would be the equivalent line of assembly that corresponds to this line of assembly, but for a different data type, right? For an integer data type. Any questions about this slide? Okay, addressing modes. Does it end there? No, right? So far this is accessing a constant index into an array. What happens if it's a non-constant index into an array? Right, so this line of code here is corresponding to array index 1. 1 is hard-coded, but usually array indexes are themselves variables, right? I want to get array index I. So how might we implement that? Yeah.
Well, you would implement, if you're working with long search, there'll be 8, but then you have to keep in mind how many indexes you're working with. So this I would probably be like 8 times I.
Okay. So the way it would be implemented is through the full, more complicated modes of addressing modes, right? So last slide, these were simple addressing modes. Next slide here, this is how we would most generally implement array accesses of a variable number of indexes in, right? So this is the complete syntax. I have my base as before. RB is the beginning of the array. I now pass in yet another register value, right? Another index register, which stores the variable index in, right? Array index I. So suppose I have an integer array, I want to access array index I, and I suppose is 3, right? I want to get index 3. How many bytes into the array would that be for an integer array? Yeah, just shout it out. 12, right? It's not just a single byte in or 3 bytes in, but rather every index is multiple bytes. So 3 indexes in, that's 12 bytes in. And the way that it implements this scaling is through the final parameter here, capital S, which says you have your index stored in RI, the register is specified at RI, how much should that be scaled up for it to correspond to the actual memory location beyond the beginning of the array? Yeah.
That's based off of what the data type of the array is. So like, because that has different size, it's based like each thing in the array is a different size. So like the scale is based off of the size of.
That's right. So what you just answered is, on the slide, it begs this question, why these numbers? Well, these numbers is exactly as you say, right? Based on the data type of the array, the variable index into the array has to be multiplied by some scale for it to be correct. Good. Questions here? Questions here? Yeah.
So wait, D is actually a number that you want to remember. It's not the letter you put. You replace D with the number of bytes you want to move.
So D here, what does D's correspond to? D is what we had on the last slide here, just the displacement. So displacement is a constant displacement in. Okay, so this should be clear working through a couple examples here. So this is a worked example showing that suppose I have 2 registers, they store these different values at a given moment. The addressing mode expressions for each of these would result in addresses expressed here, right? So here it's RDX plus a fixed constant. Here, this is RDX plus a variable value stored in RCX, so it's 0xF000 plus a constant 0x100, so it performs this calculation. Here, the variable index has been scaled up by a factor of 4. 4 bytes to an integer, 4 bytes to a float. So whatever is stored in here, RCX, 0x100. What is 0x100 in hex? Yeah. Yeah, it's 0 in the 1's digit, 0 in the 16's digit, a single 1 in the 256 digit. So this is saying I have an array beginning at address location 0xF000, and I want to access array index 256. I have my square brackets, I have 256 in the variable value. And the array, what's the array type? Array type could be ints, could be floats, because each index is 4 bytes beyond the beginning. Right, so that's this worked example here. And you can combine all of these things too, right? So you can also have something that has the constant displacement and also the multiplication factor. Questions about this slide? Yeah.
So if I wanted to run that examine function on one of those expressions on the right, would I have to like do the math myself and then put on like address? So if I wanted to like say examine what 0x8 parentheses RDX was, would I have to do the examine function with the expression on the left, or would I have to put in 0xF008?
So your question here is, what is the way to examine some other address other than the what's immediately given? I'd have to double check the documentation on that. Yeah, there's a way to do it. So the place I'd refer to is check the supplementary reading. There is a way to do that. Yeah. Okay, so the next sequence of slides, right, really is just to tie the conceptual parts from the past couple slides into the specific code examples. Right, so here I have the code that you can see from addressingmodes.c. I have the C code that you can find there, and the assembly code that I would compile to. So here, why is this corresponding to RDI? Right? We can study this already, right? This function call here, it takes as an argument a pointer. The pointer is stored in RDI, so again, the first argument to functions will be passed into RDI, and it's a move a value 0x ffffff, right, corresponding to the signed value of -1, and put it into the dereference location of pointer. Right? So pointer comes in as RDI. Here, treat that location as an address and put it into main memory. And here, concrete example, the pointer value, the array comes in as pointer, and here I have the constant offset, constant index of 1 into the array. This is a long array, so index 1 corresponds to 8 bytes, so it's 8 bytes beyond the beginning of the array. Right, so this just summarizes, you can see this for yourself. You can compile all these versions of the code for displacing a character, displacing a short, displacing an integer array, displacing a long array, and you can see that the code is always consistent, right? It does the correct thing, picks the correct flavor of the move instruction, and it picks the correct offset to make the code correct. Quick poll here, yeah.
I was going to ask, like, is it a good idea to say, like, oh, move B corresponds to characters and move W corresponds to short, and so on? Or should we, like, stay away from that mentality?
That's basically what you said is correct, right? That's reverse engineering in the sense that if you're moving a byte, well, moving a byte, what's a typical byte-sized data type? Characters. What's a typical word-sized data type? Shorts, shortens, right? So there's a correspondence between the data type and the valid move instruction involved. The thing I want to draw attention to here is why then, like I said, if I claim that each of these instructions, all of the things are kept consistent, why is it that this first argument is always RDI? Yeah.
64-bit, so my memory addresses are 64-bit.
So the point, as you said, is correct, exactly right. The actual length of the data type here, these are actually all just pointers, right? Even though what they're pointing changes, what they're pointing at changes, the fact that they're all pointers, they are all 64-bit memory addresses. So that's why the RDI here is always the DR version of the DI register. Okay, right, so the slides continue, just basically repeating the same claims about how each of these implements different array accessing modes. So here now we have the variable array index, and then you can also do array index plus a constant offset, right? So this is the ultimate example of it where we combine all of these things together, and it implements it as your base, your array starts at RDI, Your index comes in as the SI register, the second argument to the function. That has to be scaled up by 8 because it's a long array. And then also there's a constant offset beyond that because we did a +1 here. Right, so this is how it ties all these things together to use a single line of an addressing mode to implement a whole array index, array accessing scheme, such as this here. Okay, so that concludes the 2 addressing modes example, and we'll come back on Tuesday to study some more. Yeah.
I'm seeing like compare like